Hello. My name is Anne and welcome to today's video. I'm going to be talking all about Eulerian graphs, but before I get there, I just want to ask you one thing. If you find this video helpful, please give it a like or share it with someone else who you think will also find it helpful. Anyway, with that said, let's get straight into it. So last lesson, I introduced to you Leonhard Euler, the papa of graph theory, and I mentioned this Königsberg bridge problem, which he famously presented a solution to in 1735. Now, the context is that back in the day, okay, we're talking about 17th century here, the citizens of Königsberg would walk around town and with nothing else better to do, they wondered, is it possible to walk through the town in such a way where you only cross each bridge exactly once? Now, I'm not going to spoil the solution for you just yet because we are going to revisit this problem later on in the video. What I will talk about is how Leonhard Euler approached solving this problem. And he basically reduced it right down to its core of 4 land masses and 7 bridges. And he realized that you could display this information geometrically. Do you see where I'm going here? He displayed this information using vertices and edges. And it was at this point in time that he became the father of the branch of graph theory in mathematics. Anyway, we will get back to this because right now I want to talk about the context that matters way more to me, this house right here. I can't be the only one who spent my childhood challenging all of my friends to draw this X house without retracing any lines and also without picking your pen off from the page. I don't even know how many hours I spent redrawing this house again and again and again until I finally found a solution. And I'm pretty proud of myself because the solution that I came up with when I was a kid coincides with what we're going to learn today. And yeah, this is a problem that we're going to get back to later. Now, if you don't recall what the difference is between a walk, a trail, and a path, I highly recommend you go back to my introduction to graph theory video where I talk about these things and also where I first bring up this graphic that can help you distinguish between the 3 walk, trail paths. We're going to be focusing on this section here, trails, and also how they can be Eulerian if every edge is traversed. Now, of course, I'm not going to leave you completely in the lurch. I will remind you that a trail is a walk where edges cannot be repeated, but vertices can. And the new but very important concept for today is that a trail is Eulerian if it visits every single edge of that graph, okay? This is really important. A trail is Eulerian if it visits every single edge of that graph. Now, to add a little bit of vocab to that ever-growing list, an Eulerian trail can either be open or closed. Closed meaning that it begins and ends at the same vertex, open meaning that it begins and ends at different vertices. Now, if an Eulerian trail is closed, the term that we use to refer to it is actually Eulerian circuit. I mean, you can still use closed Eulerian trail, but we more often refer to it as Eulerian circuit. And if the Eulerian trail is open, then we call that a Semi-Eulerian trail. But again, you can just use open Eulerian trail and closed Eulerian trail if you really want. Now, on the screen here is a little summary of what I just spoke about. And I do want to point out that when you see the term Eulerian trail, it does include both the Semi-Eulerian trail and the Eulerian circuit. So you do have to be aware of that, especially in an assessment. Okay, so now we have laid the foundation to understand what the difference is between a semi-Eulerian graph and an Eulerian graph. But obviously we're going to start with a semi-Eulerian graph. So a semi-Eulerian graph is one that is, first of all, traversable. Now this is a really useful term because it's just one word to mean that it's a graph that can be drawn without lifting your pen off the page or retracing any lines. Second of all, a semi-Eulerian graph contains a semi-Eulerian trail only. If it contains an Eulerian circuit, it's actually going to become an Eulerian graph, not a semi-Eulerian graph. So the most that it contains is a semi-Eulerian trail, aka an open Eulerian trail. And the third thing that is specific to a semi-Eulerian graph and is super useful for finding out if a graph is Eulerian or semi-Eulerian or not is that a semi-Eulerian graph has exactly two odd vertices, no more, no less. And it's actually that third condition there that was one of Leonhard Euler's findings in his solution to the Königsberg bridge problem. Anyway, on the screen here, I've got a graph where I'm going to show you what a semi-Eulerian trail looks like. I do have the start and end vertices labeled already, and you'll notice that they are different because it's an open trail. It doesn't begin and end at the same vertex. So the trail starts at A, goes to B, around to D, C, D, E, A, C, and finally ends at B. Now that is a little messy, but you can see that every single edge has been traversed. And so this is an Eulerian trail. And because the trail begins and ends at different vertices, in this case A and B, this is an open Eulerian trail, aka a semi-Eulerian trail, which makes this a semi-Eulerian graph. And before we move on to Eulerian graphs, I better show you how this semi-Eulerian graph has exactly two odd vertices. So whenever I count the degree of a vertex, I like to visualize drawing a circle around it before counting the number of edges. So I've got 1, 2, 3, and 4. This vertex has a degree of 4. C also has a degree of 4. B has a degree of 3. A has a degree of 3. And E has a degree of 2. Now, what you may notice is that there are 3 even vertices, and then there are exactly 2 odd vertices, A and B. What else does that coincide with? That is the beginning and the end of the semi-Eulerian trail, and this holds true for all semi-Eulerian graphs. The 2 odd vertices is where you'll find the semi-Eulerian trail beginning and ending. Now moving on to Eulerian graphs. The 3 conditions that need to be met for an Eulerian graph are comparable to the semi-Eulerian graph. The first condition is exactly the same, where the graph needs to be traversable. The second condition is slightly different, however. We're looking for a graph that contains an Eulerian circuit, not just a semi-Eulerian trail. And the third condition, which is another one of Leonhard Euler's findings, is that Eulerian graphs have vertices that are all even. On the screen here, I have a graph where I'm going to show you the second and third condition. I'm going to start with the all even vertices. So, starting with vertex A, that has a degree of 4. Vertex B has a degree of 4. Vertex C also has a degree of 4. Vertex D also has a degree of 4. And last but not least, vertex E has a degree of 2. So notice that all of the vertices are even. Now I'm going to switch to my highlighter to show you the Eulerian circuit. Now, with a semi-Eulerian graph, the two odd vertices are the beginning and the end of the semi-Eulerian trail. In an Eulerian graph, you can start and end at any vertex because they're all even. So I have just chosen to start with vertex A in this case. So I'm starting with A, traveling to B, over to D, C, D, E, A, C, B, and instead of finishing there, I'm gonna end with this new edge that was added to get back to A. So this is an Eulerian circuit. You can see that every single edge of the graph has been traversed, and the trail begins and ends at the same vertex. Okay, let's get stuck into some examples. So this first one asks me to classify the following graphs as Eulerian, semi-Eulerian, or neither. Now, when I do these questions where I'm determining whether a graph is Eulerian, semi-Eulerian, or neither, I like to start by calculating the degrees of every single vertex and going from there. So for my first graph, this vertex has a degree of 2, this one has a degree of 4, 4, 2, 3, 4, 5, 6, 3, and 1. Now, when I look at all of those vertices, there are exactly 2 odd vertices, which tells me that there's going to be a semi-Eulerian trail, which needs to start and end at the 2 odd vertices. So let's just check that. I might start with this odd vertex and just trace along the edges until I get to the end. So this graph is semi-Eulerian because it contains a semi-Eulerian trail only. It has exactly 2 odd vertices and it's traversable. Now, moving on to the second graph, I have a degree of 3, 3, 4, 3, and 3. Now, I have more than 2 odd vertices. Straight away, this one is going to be neither. And moving on to my third graph. So I've got this vertex has a degree of 4, 4, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, and 2. All of the degrees are even, which tells me that this is probably Eulerian. Just double checking with an Eulerian circuit. So starting anywhere and tracing along until I end where I started. So that contains an Eulerian circuit, has all even vertices, and is therefore, and is traversable, and is therefore Eulerian. Okay, moving on to the second example, which is just a word problem. So Alex Concreting Business recently won the bid to replace all the footpaths at a local theme park. The network below shows the footpaths that exist between the 7 attractions. So here's our graph. Our attractions are the vertices A, B, C, D, E, F, and G, and then all the edges represent the footpaths. Part A asks us to use mathematical reasoning to determine whether Alec and his team can pour the new concrete in such a way that they don't retrace any paths, nor do they need to relocate the concreting equipment during the pour. So this is the type of word problem that may come up that's insinuating an Eulerian trail. Now, what I'm thinking about here, or what I'm noticing as I'm reading this context, is that we want to pour concrete on every single path, every single edge, Eulerian, okay? They all start with E. Write something down that'll make you remember that, okay? Now, the other two things that support that is that we don't want to retrace any paths and we don't want to relocate the concreting equipment, meaning that we don't want to pick our pen off the page to move to a different section. So it's asking us if this graph is traversable, and then we can go one step further to say whether it's semi-Eulerian or Eulerian. So I have the graph copied down here and I'm going to check whether it's Eulerian or semi-Eulerian. The place that I'm going to start is by checking the degree of every single vertex. So starting with vertex A, that's got a degree of 4, B has a degree of 2, C has a degree of 4, D has a degree of 3, E has a degree of 4, F has a degree of 3, and G has a degree of 4. Now, when I look at all of these vertices, I can see that there are exactly 2 odd vertices, which indicates to me that this graph is semi-Eulerian. Let's look for that semi-Eulerian trail, starting at one of the odd vertices and tracing along until we cover all the edges and end at the other odd vertex. So this graph is traversable, it contains a semi-Eulerian trail, and it has exactly 2 odd vertices. So this graph is a semi-Eulerian graph. So to answer the question, Alec and his team can pour the new concrete in such a way because the graph is semi-Eulerian, and that's what I'm going to write down. Alec and his team can pour the new concrete. The graph is semi-Eulerian. Now, I will go one step further and state that it is traversable, contains a semi-Eulerian trail only, and has exactly 2 odd vertices. Now, moving on to part B, state the route that Alec and his team should take to reconcrete the footpaths. Okay, well, I actually found the semi-Eulerian trail earlier. I'm gonna erase that and highlight as I write down the walk, or the trail in this case. So I'm starting at F, and then I'm going to A, and maybe I'll go to B, C, F again, G, C, D, E, gosh, this is a long one, A, back to E, over to G, and finally we end at D. Now that wasn't exactly the same as the semi-Eulerian trail that I mentioned earlier, or that I showed earlier, but that's fine. It starts and ends at the odd vertex and covers every single edge. Okay, moving on to the last example for today, which is a revisit of the Königsberg Bridge problem. So part A asks me to label the land masses A, B, C, and D, then construct a network to represent the Königsberg bridges. So I'm going to start by labeling the land masses A, B, C, and D. Now I'm going to use vertices to represent the land masses and edges to represent the bridges, which means that I need 4 vertices, A, B, C, and D. And now I'm going to add the edges in to represent the bridges. So I've got 2 bridges between A and B. I've got 2 bridges between B and D. I've got one bridge between C and D, one bridge between B and C, and lucky last, one bridge between A and C. How nice is that? That is my completed network to represent the Königsberg bridges. Okay, so part B now asks us to use mathematical reasoning to determine whether it is possible for a citizen of Königsberg to walk through the town in such a way that each bridge is crossed exactly once. So in this case, we're either looking for a semi-Eulerian graph or an Eulerian graph. It doesn't specify that the townsperson needs to begin and end on the same landmass. So you don't really need an Eulerian graph. The very minimum that we're looking for is semi-Eulerian. So I have my graph from above copied down here, and now I'm going to check whether it is Eulerian or semi-Eulerian. So I'm going to check all the degrees of the vertices. Vertex A has a degree of 3. Vertex B has a degree of 1, 2, 3, 4, 5. Vertex C has a degree of 3, and vertex D has a degree of 3. Okay, well, this is definitely not Eulerian because all of the vertices are odd, and it's definitely not semi-Eulerian because we don't have exactly 2 odd vertices. So I'm going to state here that it is not possible to walk through the town only passing through each bridge exactly once. Since the graph is neither Eulerian or semi-Eulerian, it is not possible to walk through the town in such a way that you only cross the bridges exactly once. Part C now asks us to state the modification that needs to be made to the graph so that there is an Eulerian circuit. So looking at this graph, well, all the vertices are odd and I need them all to be even for there to be an Eulerian circuit. So I'm going to add one edge connecting 2 of the odd vertices, which makes those even. And I would need to add one more edge between the other 2 odd vertices, which would make those vertices even. So the modification here is that I'm going to add 2 edges. In this case, that's A, B, and CD, but you can also add A, C, and BD. And the reason why I'm doing that is so that all of the vertices become even, and then there will be an Eulerian circuit. So let's double check with the new added edges. Starting anywhere, I can trace along the edges. And end where I started. I've covered every single edge. It's traversable. There's an Eulerian circuit. Edge AB and CD need to be added to make all the vertices even and therefore contain an Eulerian circuit. All right, guys, the very last thing that we're going to look at before I finally get to the end of this video is my childhood challenge. So I'm just going to check whether the graph is Eulerian or semi-Eulerian. But before I do that, I'm just going to highlight where the vertices are. So I've definitely got vertices here in the corners. I can add a vertex here at the top. And I could add a vertex here in the middle, but it's not necessary because I see those 2 edges. Oops. I see those 2 edges as intersecting. Now, I need to check the degrees of each vertex. So at the top here, I've got 2, 4, 3, 3, and 4. So this graph has exactly 2 odd vertices, which tells me that it's semi-Eulerian. That means that there's going to be a semi-Eulerian trail that begins at one of the odd vertices and ends at the other odd vertex. And that is exactly the solution that I figured out when I was a kid. I didn't really know it was semi-Eulerian or Eulerian, obviously, but I knew that if I started from one of these 2 corners down here at the bottom, I'd be able to draw the whole thing. And that's all I have for you for Eulerian graphs today. If you found the video helpful, just a reminder, you can support the growth of this channel by giving the video a like, subscribing, or sharing this video with one of your friends. All right, I'll see you in the next one where I'm going to be talking all about Hamiltonian graphs. Bye.